Welcome to lesson number 1 of relations. We're going to be looking at the Cartesian coordinate system. And the Cartesian coordinate system is a 4-quadrant graph. And this 4-quadrant graph is going to look something like this. And this first quadrant here, where all values are positive, is quadrant number 1. Over here, 2, 3, and then quadrant 4. Now, in this example, we want to find each of these coordinates, A, B, C, D, and O, and we want to label what their coordinates would be on the grid. So if I find point A, or coordinate A, I find this value here, and we always list it in terms of X and Y. So X going first and then Y. Now my X value here is 2, and my Y value going up is 1, 2, 3, 4. So I would plot that at 2 and 4. And then I would do the same for the following coordinates. So coordinate B is at 1, 2, 3, negative 3 on the x-axis, and 0 on the y-axis. Coordinate C is at positive 6 on the x-axis and negative 3 on the y-axis. So 6 and negative 3. Coordinate D is at 0 on the x-axis but negative 3 on the y-axis. So 0 and negative 3. And finally, coordinate O is at my origin. So that's O for origin, and that's at 0 and 0. Now, write the coordinates of the point in the second quadrant. Now, I only have one coordinate in quadrant 2. That's quadrant or coordinate E here. So that's E, and that's at negative 2 and positive 3. So negative 2 and positive 3. Now we want to write the coordinates of the point in quadrant 3. Here's quadrant 3, and that's point F, and that is at negative 4 on the x and negative 3 on the y. Negative 4 and negative 3. Now, if I complete the following table using positive or negative, so in quadrant 1, all my x values are positive and my y values are also positive. In quadrant 2, my x values are negative while my y values are positive. Quadrant 3, they're both negative. And in quadrant 4, my x values are positive while my y values are negative. Now, whenever we have a linear relation, we can describe them pictorially, or we can use an equation to explain what's happening within a diagram. And so we have 3 toothpicks that are used to form a triangle, and anytime I want to form another figure or another triangle, I need to add 2 more toothpicks. So here's 3 toothpicks. Here I have 5 toothpicks. Here I have 7 toothpicks. So I've added 2 each time to get another triangle. Now if I wanted to draw the next 2 diagrams in the pattern, so here's figure 1, 2, 3. Figure 4 would have 1, 2, 3 plus 2 plus 2 more plus 2 more toothpicks. Figure 5 would look very similar, so starting with 3 plus 2 plus 2 more plus 2 more plus 2 more. That's what figure 5 would look like. Now you want to complete this table of values. So figure 1 had 3 toothpicks, while figure 2 had 3 plus 2 was 5, which means that figure 3 has 7, and we can even count 1, 2, 3, 4, 5, 6, 7. And every time we're adding 2 toothpicks to our total. So figure 4 and figure 5 had 9 and 11 respectively. Now what we want to do is we want to represent our data in our table of values. We want to represent it on the grid. So here's my grid, and I'm going to take my my values from my table and I'm going to input them onto my graph. And so if we call this our origin, 0 and 0, this is all in quadrant 1 because our values are all positive. I could increase by a scale of 1 on my x-axis, and on my y-axis I'll probably want to increase by a scale of 2. So at 1 and 3, if I call this my t value and these my p values, according to this graph, So when I'm at when I have one toothpick triangle, so one triangle, then I have three toothpicks. So that'd be a 1 and 3. When I have two toothpick triangles, that would be at 2 and 5. Next would be at 3 and 7, 4 and 9, and 5 and 11. Now explain why it does not make sense to join the points in a straight line. So I'm not going to have any toothpick figures between 1 and 2, so there's no figure 1.5. And since there's no figure 1.5, I also don't have any data at when I use 4 toothpicks. So the number of toothpicks does not include, I guess, partial triangle figures. Partial, I'll call them toothpick triangles. Now I want to, this means this is discrete data as well. So this is discrete data, means it's not continuous. So there's no information in between each of our triangles. Now we want to describe in words the relationship between the number of toothpicks and the number of triangles. So the number of toothpicks is, well, it's double the number of triangles plus 1. So for example, when I have one toothpick, if I were to multiply that 2 by 2, that would be 1 times 2 is 2, but plus 1 would be 3. 2 times 2 is 4, plus 1 is 5. 3 times 2 is 6, plus 1 is 7. So to get a number of toothpick, then it's going to be equal to 2 times the number of toothpicks plus, or sorry, 2 times the number of triangles plus 1. So use the equation to determine the number of toothpicks if there are 27 triangles. So if t is equal to 27, then we would have to input it into our equation, which is p is equal to 2t plus 1. So p is equal to 2 times 27 plus 1. So p is equal to 54 plus 1, and p is equal to 55 toothpicks. In this next example, we have a student in a physics classroom. He's determined the resistance in electrical current by measuring the voltage V when a current, or I, was passed through the circuit. The table shows the following results. So 0.5 to 6, 1.5 to 18, 336, 3.5 to 42, and 448. First thing we want to do is represent this data on a graph. Now, the first thing you'll want to do is look at where each of these are located. So we want I, which is our current in amps, and our voltage in volts. And so generally speaking, these are organized as X and Y. And so we're going to want to have our current down here on the X-axis, and this is our current in amps. And then that means that we're going to have our voltage up here. So I'm just going to write V for voltage so I don't get too much in this space here. So the next thing we'll want to do is determine how big our scale wants to be, how big we want our scale to be. Now, if I look at how this graph is kind of split up, it's split up into chunks of 1, 2, 3, 4, 5 squares. All right, and if I look at my data only goes up to 4 here. And so I could go 1, 2, 3, 4, and that leaves me with a little bit of space to work with my origin being here at 0, 0. Now, when I'm at 4, I'm up at around 40 or 50, right? So here I have 1, 2, 3, 4, 5. So it might make sense to increase by 10. So 10 20, 30, 40, 50. Now we want to graph our points. So my first point at 0.5 and 6. So if I'm going 2, 4, 6, 8, or 0.2, 0.4, 0.6, 0.5 would be in between here. So 0.5 and 2, 4, 6. That's my first point. My next point is at 1.5 and 18. So again, I got 1.2, 1.4, 1.5 would be here, and 18 would be here. Next, I'm at 3 and 36, so this is an easier one to plot, but 3 along this line, plus 2, 4, 6. 3.5 is going to be in between, and 42, so 3.5 and 42. And then, so 3, let me make sure I got that, 3.5, good. And then we had 3, and then 1.5, and then 4 and 48, we're going to be right here. Now, does it make sense to join the points together with a straight line? And now we want to explain. Well, in this case, yes, it does make sense. So, but when there's no current flowing, that's going to be 0, so we'll also have a voltage of 0. And if I were to look for other points, because the current is going to be flowing continuously through this circuit, then there's going to be in-between points. So for example, I could have a situation where I have 2 amps flowing, and that'll correspond to a voltage of around 24. So in this case, it does make sense to join this in a straight line. And this is going to flow continuously. So yes, and that's because the data is continuous. So there are intermediate points in between the data that's given to us. Now I want to use the graph to determine the voltage for a current of 2.5 amps. So 2.5 would be right here. So if I go up, 2.5 would be here. So at 2.5, I'm around. Actually, sorry, I should be around 30 here. So if I actually use a ruler, at 2.5, I'm actually supposed to be on 30. And so if I were to graph this like I should have in the first place, this is where that point lands. So this would have a voltage of 30 volts. Now we want to write an equation expressing volts in terms of our ampage. And so volts is equal to, well, let's see how this changes each time. Well, if I look at the difference between all of these, so 6 to 18, that's going to be a difference of 12.